let's come back to this and let us finish off this segment itself. So we have discussed we are in the process of discussing the preliminary attributes with respect to mathematical fundamentals on cryptography. So last day we had discussed a lot of with respect to groups and their properties. So keeping that in mind, let us move ahead with the next one, which is not working here. Okay. Right. So it's showing something else to me. Anyway, so group property verification. I'll write it. So in this group property verification, this actually we had taken examples and we had tried to prove the 5 properties. If you remember, we had 4 properties which is supposed to be met by any group. Along with that, if the commutative one also is taken care of, then we will call it as an abelian group, right? So that's the basic example. This we already had taken, so we don't need to merge much over here. Now, this is where we actually start off with a discussion, which is part of, again, group, and that we call as a subgroup. All right. Now, as you can observe over here very clearly, just for example, just a definition, if you call it, that if there are finite number of elements in a group, we will call it as a finite group. This finite group definition will come today itself handy when we discuss about the Galois field, which is in fact called as GF field. Those who have done, anyone here did information theory and coding? You are doing right now, is it? Okay. So when you are doing the error control coding, which will come, I think, in the 4th to 5th module, I think, error control coding, linear block codes, cyclic codes, Viterbi algorithms, you will find the application of fields there also, or rather the Galois field there as well. All right. So in error control coding, what is the basic purpose? Is that, guys, can you please listen to this? The problem is that here, the groups that you are discussing, this leads to ring as well as fields. So after we have done the field, you will find, or you will observe that the fields will have certain properties based on which a specific category is Galois field. And that particular application, if many of you, in fact, in F1 as well as for F2, were discussing, like asking me that, sir, where is the application of them? You will find that especially those who are doing information theory and coding, you will find when you are doing the error control coding, the application of this Galois field, the groups will come there as well. Alright, so it's an overlapping scenarios there. I used to take information theory and coding a long time back, but I could have given that insight also to you. But for the time being, we don't need that for cryptography as much. So please, so you can look into that as well. But later, but for the time being, so if there are finite number of elements in a group, we will call them as a finite group or else infinite group. And the number of elements in a group is called as the order of the group. That's very, very important. This order of the groups will be used for discrete logarithm calculation, the last part of this segment, which I don't think will be covered before the Cat 1, but it will be useful later on. Keeping that in mind, just that gives me a note, like information. For example, I have given the, suppose I go back to this one only, you can take the example here also. You can see the group that is given Z10 comma plus sign, like plus is here operator over here. Now, as I already have told you that Z10, what kind of a group it is? Is it a additive group or a multiplicative group? Z10, the one that is mentioned over here. What was this nomenclature that I told you? If it is a normal conventional capital Z10, it means it's a additive group. And if it is a Z star 10, then it would be a multiplicative group. That's what I told you, I think somewhere back here. That's how it is related. Like this all will be referred somewhere. Okay, so this is already we have done in previous day's class. So you can see the last example. Now, in that, if you observe that if I take the first part, the Z10, and you take plus as the operator, which is being used, and you check for the process involving the properties involving groups. All right. Same way, you can apply that for the Z10 star as well, which has 1379. Now, this 1379 will definitely have an impact. Why? Because if you observe that 1379, these are the 4 possible elements which will have a multiplicative inverse for the given set Z10. But if you apply the conventional addition or multiplication on this, plus addition will never happen anyway because it's a multiplicative group. But suppose you do a normal multiplication on this set, Z10 star. Now see the element, 3 into 1 is not a problem. But if you take 9 into 7, it is going beyond the set. But as per our rule for group, if you go back to the properties of group, the element A dot B, you can see the C element should also be belonging to the set itself. So why we are calling that as a multiplicative group? Because group now we have defined with some properties. The answer to this is the multiplication which is used for a multiplicative group is not a conventional multiplication but a modulo multiplication. Alright, so that is the difference. We'll come to that sometime later. For the time being, we don't need that information. But why I am telling you this? Because if you observe carefully that this particular operation, Z10 plus, you can see that this is the question is that is this a subgroup of Z12 plus? Alright, so in that way the answer is no, because you can see the operation H is addition modulo 10, whereas operation in G is and modulo addition of 12. So although it seems like that 10 is included within the set of 12 elements, but as the modulo operators are different, the necessary outputs will be different and the operations will be different. So you can see the subset or the subgroup, how we are defining it. It is a subgroup. H is of a subgroup of G when H itself is a group with respect to the operation of G, if at all that happens. Like within G, if the elements exist and if they are following the properties of group, then that can be considered with respect to that modulo operator as a subgroup. Alright. Now keeping that in mind, now comes a cyclic subgroup which happens to be has a very interesting observation, and cyclic subgroup will play again an important role sometime later. Now cyclic subgroup, as the definition suggests, if a subgroup of a group can be generating using the power of an element, then the subgroup is called a cyclic subgroup. Now see this example, very interesting and very informative also. Now if you observe Z6 plus, like Z6 plus over here. So the elements which we have is 0, 1, 2, 3, 4 and 5. Rather 5 elements we can have over here. Now see the definition by how we are doing it. If you take the first one, you take the cyclic subgroup generated A point. Okay. The cyclic subgroup generated from 0. Now the process is A to the power n. Alright, so what we are going to do is, what does n over here means? It means that it will be the order of the modulo operator. Okay, so in this case, the example wise, it is, what is that? Example wise, it is Z6. So the order should be going till 5. So 0 to 5 is the maximum. Now how we are generating the cyclic group is given over here. See the first step, 0 to the power 0. Alright, so so the elements are, the elements that we have over here, the elements that we have over here is 0, 1, 2, 3, 4, 5. So first element we take 0, 0 to the power 0. Any element if you take with power to anything with respect to 0, it will be 0. So 0 is the first element. So you can see the process stops. Why? Because 0 is an element to Z6. So the first order, you can see the cyclic subgroup generated from 0 is H1. See, H1 is mentioned. Only one element, 0. That's how we are generating a cyclic subgroup from Z6. We'll see the example with other modulo values as well. So the H1 stands for 0. So first thing is done. Now take the next element 1. Now if you take 1, see the P calculation that we have over here. 1 to the power 0 mod 6. Alright, 1 to the power 0 mod 6, and we are generating 0. So 0 is an element to Z6 group. Then 1 to the power 1, 1 to the power 2, 1 to the power 3, 1 to the power 4, up to 1 to the power 5. After that, if you take 1 to the power 6, what will happen? So it is going back to the previous set of elements once again. That's why it's mentioned, you can see, stop, the process will proceed, not proceed. So what are the elements we have over here? 0, 1, 2, 3. If you check here, 0, 1, 2, 3, 4, 5. So this 0 to 5 is nothing but the set itself. So you can see H4 is mentioned over here. Okay, H4 is G itself. So with the element 2, we are generating the set itself. Okay, and that's a cyclic subgroup of the element 2. Now we take the element 3. of the Z6 series. So let's see. So after 0, 1 is done. Now 2. We take 2. Now you can check here. 2 to the power 0 mod 6 is equal to 0. 2, sorry. Happened. Yeah. 2 to the power 0 mod 6 is equal to 0. 2 to the power 1 mod 6 is 2. 2 to the power 2 is mod 6 is 4 you are getting. But 2 to the power 3 if you are taking, it is going beyond to back to 2 once again. Because 2 to the power 3 is 8. 8 divided by 6, the remainder is 2. So it is you are getting the same element once again. So stop the process required. So the element, the cyclic group generated by 2 will be 0, 2, 4. So that's what is mentioned in H2. You can see on the top of it, it's mentioned. So H2 to 0, 2, 4 over here. Now, if we take 3, in the same manner, we can generate an element 0 and 3. You can see the last one in the same process. Now, H3 is done. Now, if you observe the last one, now I go to 4. Now, if I go to 4, it is repeating the same thing. You can see H2 is not a new subgroup because it repeats what is already there in H2. 0, 4, 2. 0, 4, 2. This one, last one. It's already available somewhere over here. 0, 4, 2. So, when we reach at fourth element, the cyclic subgroup is not generated because it's already been generated. So, my answer is for Z6 with a symbol, with an element plus over here, the operator plus, the cyclic subgroups are given by, you can see here mentioned, 0, H2 is 0, 2, 4, then we have 0, 3 and H4. And observe carefully, in all of the cases, the operators have been mentioned properly. In each of the cases, it's plus. As I said, if the operators are different, the results will be different. Right? Now, we are aware of what are the binary operator, what is algebraic structure. So, this is the group we have defined here last class. Now, we are defining subgroup, and within that, we are defining cyclic subgroup because it's repeating the group once again. Okay, so this is the cyclic subgroup for any modulo operator that we come across. So, keeping that in mind, if you have understood this, can we find out for Z10? Okay, can we find out for Z10 over here? So, there are, as you can see, Z10, what are the elements? 1, 3, 7 and 9. 1, 3 and 1, 3, 7, 9. So, please make a note, please make a calculation of 1 to the power 0, 1 to the power 2 like that. Take each and every element and try to compute that what are the cyclic subgroup for this particular set of elements. Please check it. The elements are 1, 3, 7, 9. Just like in the previous example, we had 0 to 5. 0, 1, 2, 3, 4, 5. Here we are having a scenario where we are keeping in mind that we have 4 elements, 1, 3, 7, 9. So what I want you to do is something like this. Just see for yourself, you will be able to understand. So first thing is we're taking 1. We are taking first element 1. 1 to the power 0 is, 1 to the power 0 is 1. Alright. And after that, if I take 1 to the power 1 or 1 to the power any element, you can see the result will be the same. So basically the first element, after that it stops. So for the first case, you can see the cyclic subgroup H1 has only one element 1 and the operator that we have is multiplication, because as I said, Z10 star is a multiplicative inverse group. So this cross that you are looking at, this is not a normal multiplication, but a multiplicative modulo operator. Alright, so that multiplication, see the sign there, okay, cross sign. Usually for the normal multiplication, the way we do it, it should be a star represented. Here you can see it's an X kind of a cross that is given. So that sign indicates, ideally, this sign that that you are looking at, cross over here, this actually stands for the modulo multiplication operator. Alright, so we'll see that sometime later maybe. But for the time being, what happened here is that for the first case, you can see H1 has only one element 1 and the operator that associated with it is multiplication. Alright, modulo multiplication, we would say. Now next element we take 3. So you can see the 3 taken over here, 3 to the power 0 mod 10. 10 has changed, mod has changed because the multiplicative group itself has Z10. So the base is 10. Okay, so that's my observation. So over here you can see 1397 is repeated. So you can see 1397, this happens to be the group itself. So you can see H2 over here. This 1397 is nothing but H3. You can see the last element over here. Understood? So what my observation is that for each and every element, we are going to go on increasing the power. So suddenly, one lines form a set over here. As we are repeating, as we are getting the same element, because you can see 3 to the power 4 mod of 10. What will be the output? 1. 81 divided by 10. So remainder is 1. 1 is already there. So we stop the process. So as the element over here has already been received, so for cyclic subgroup generated from 3, element 3 will be nothing but H3 of the group itself. As at least here it is that like that. Now if you go to 7, 179 again you can see. So it is basically the same group once again. So we can neglect that. We don't need to have that because it is very similar to the previous example where when we taking 4, it was going back to the previous one. So we can neglect this one. This is same, we have already defined here itself. These two are same. Only the permutations have changed. 9, can you do it? The last element 9, what are the cyclic subgroup you are getting? Please do it. Cyclic subgroup for 9. 9 to the power 0 mod 10. 1. Right? 9 to the power 1 mod 10. 9. 9 square 1. 1. So we are getting basically 1 and 9. Okay, after that we can't go anywhere. So for this, the set will be 1 and 9. See the H2 over here. 1, 9. So basically, in any of your question like this, you will be given a particular group and a particular operator which you need to use and find out that whether they belong to any subgroup or it does have the cyclic subgroup. If it has the cyclic subgroup, what are the subgroups present? Okay, so now this is for 10. If suppose the number is more, so naturally you will have more number of cyclic subgroups. So that's the process to involve. But as I said, these are all specific, I would say, mathematics that is there as such for the time being. But as I said, going on telling you, the third, fourth module when we discuss post Cat 1, you will find the application areas of this. As I was telling you, one of the cases for fields, you will find it in information theory and coding. So that's how you relate the two stuffs for that matter. Right? So that's all about the groups for that matter. Now we come to ring. Alright, now ring and fields are like part of like extension of the group what we look into. Just take the condition. That's the most important part. So you can see a set of numbers with two operations, addition and multiplication in some form, and it has the closure property and is associative and the distributive law if it is maintained, then we can claim that group as a ring as well. Alright, so if these properties are maintained and if along with that the commutative group, you can see commutative operation is also maintained, then we can say commutative ring. Remember, the proofs that we have done previous day, we had taken only one binary operator, z comma plus or z comma multiplication like that. But suppose there are two operators on that particular set which has the following property: closure, associative and distributive. Then we can call that particular group as a ring. And along with that, if it has a commutative one, which in that case was abelian group, here it will call that as a commutative ring. Ring, that's the term that we come across. I'll show you a diagram along with this. So if multiplication operation has an identity, no zero divisor, it forms an integral domain. This is just a name. Just for the time being, keep it with you. This is the diagram to explain that. If you observe carefully, this diagram, the first operation should make an abelian group. The second operation should make at least a semi-group. It doesn't matter, the second group doesn't have all the properties intact. If you check the diagram over there, okay, there is two operators. One is that dot, black color spot, and the other one is the square, the box that you're looking at. So box and dot are the two operators. Anything. It can be plus minus, it can be plus multiplication. Just imagine in that way. So this dot and the box are the two operators which forms a ring. Now if you observe the dot over here, the black dot over here, it contains all the properties. Closure, associative, commutative, existence of identity, inverse, all these properties are maintained. That's why it's mentioned in right hand side. The first operation should be an abelian group because it contains all. Remember, abelian group, commutative also it should follow and all the four properties will have. So that's why it's mentioned. But you can see right hand column over here, the box, white colored dot over here. That actually has closure, associative and commutative. Alright, so that's how the ring is formed and the properties are maintained. So groups we discussed with 5 properties for different reasons proved. And now ring is nothing but addition of another operator. Both operator has some certain properties and certain application on the set of elements. Then we call that as a ring. Why ring is important? Because ring will give us the understanding of field, which is the third part of it. So let's go directly to field for that matter. Now this is what about the field. Now if you see a set of numbers where two operations, you can see which the difference is abelian group for addition, abelian group for multiplication, ignoring 0, and it has to be a ring. Okay, so it has to be a ring. That means two properties should be there, two operators will be there, but both of the properties will match to being an abelian group. For that matter, you can see the last diagram. Group will give us ring will give us field, and field will give us the polynomial arithmetic after some time. Alright, so let's, with the diagram, if I explain you once again, same way. So we have the elements over here. Now again the same way, the dot and the square or the box is basically two operators over here. Now if you observe here, both the dot as well as the box are following all the 5 properties. So that's the difference between a ring and a field. Okay, it has, in the field, for a field, it has to maintain all the properties along with it. So that's the idea. So both the operators should fulfill all the properties. If not, then it is a ring. If any one operator is maintaining, then it becomes a group. So group, ring and field. So in that way, if I go on, this is basically what the observation should look like. Alright, so this in fact very similar to what we had discussed with respect to group, if you remember. So with respect to this properties, closure, associative, additive and inverse, this if it is maintained, when we call as a group, with respect to addition for that matter. But now along with that, if the commutative also is maintained, then we call it as an abelian group. Now if you have two such properties, you can see M1, M2, M3. So one is addition operator, one is multiplication operator. If that is maintained, we call this as a ring. If within that ring, any one, the second operator of is maintaining the commutative property, then we call it as a commutative ring. And along with it, and if all are maintained, then we call it as a. Alright, so that's how the span of action which happens with respect to different operators. Alright, so this is about the basic understanding about groups and its property and leading towards ring and field. Now, why field we are talking about? That's the next slide that we have. This is where the polynomial arithmetic will come in. I guess all of you will be relatively comfortable in solving this kind of question. Why we require is that whenever we have, like practically, if you ask me, suppose you have a long digital data, large set of digital data. It's imperative that you won't send the whole set of bunch of data over the channel. The very reason is that if you take suppose there's 100 or 1,000 odd data that you have and you are sending all together, basically there will be a lot of bandwidth requirement also. So in order to do that, what will happen, and even the processing also will have hamper in that way. So what you will do is you will divide it into some blocks, some block of data. Okay, so that block is basically the information theory and coding where you discuss linear block codes. As I said, third, fourth module, most probably fourth module you have in ITC, will have block codes. In block codes, what happens? There is a portion of message. Please understand this carefully. A portion is message and the other part is parity. Now, why do we send the parity bit is whenever you are sending from transmitter to receiver, this parity bits will be checked. That as if the data is properly sent and received or not. Forget about cryptography. Cryptography is within the data you are hiding something or you are making it changes. That's a separate part. But if the data or the message itself is corrupted, then the detection will also hamper, right? So for that, for any communication system, you require an encoding technique. Understand? That whole process of encoding depends on how your finite fields, how you are defining those binary data into field format. This fields. That is the practical most application for polynomial arithmetic and how we define it. Because based on this polynomial arithmetic, you will define the digital circuit also. So VLSI is also limited to that. Embedded system comes in handy. What will be the memory size? What will be the number of flip-flops being used? So all those are dependent on the error control coding and the block codes being used. But what is the fundamental background to block codes is the polynomial representation or polynomial arithmetic that is being discussed over here. Unfortunately, the other part is not the part of cryptography, so we can't discuss that. But this is the fundamental mathematical part of the whole setup. Right? So if you see, Galvez showed that for the field to be finite, now we know finite field that there are finite number of elements we present. Now for most of the cases, what will happen in our case, binary data, if you consider 0 and 1, so those are the two elements which will be present in a set. That's a finite field. We will represent that as GF, I think it's mentioned GFP. You can see over here. Okay, in general, this is GFP. Or in general, it is mentioned as GFP to 2 to the power n, where n will become the n positive integers mentioned over there itself. Alright, so suppose you have n is equal to 4, it means 2 to the power 4, or you have 16 odd elements which will be taken all together. And we will have to represent the polynomial expression with respect to those 16 elements present. Alright, so let's see how it goes. So a Galvez field, we call it the Galvez field. Okay, the pronunciation is like that. GF p to the power n is a finite field with p to the power n elements. Alright, so let's see one by one. Okay, so this is about this. Now this is about the definition of it. I don't think we need that much definition over here. They also follow the extended Euclidean algorithm. See why we have discussed extended Euclidean algorithm somewhere back. The application of it, right? So that's why I was telling you that sometime down the line you will need to use those elements. So this is where we are using it. So GFP is the set of integers with arithmetic operation modulo prime p. Okay, so all the operators applicable to Galvez field will be modulo operator itself. Now let's see about the first example when we take n equals to 1. So basically there are two elements 0 and 1. You can see over there, and that itself, you can observe that we have formed a tabular approach. In fact, this one, the table that you're looking at. Okay. Now you can see that there are operation, addition and multiplication. As it is a field, we are assuming that addition and multiplication are two operators which has the certain property. The 5 properties are maintained only. So that's why the concepts of field and rings are being studied. Alright. Now if you see the table, this is also in fact called Kelly's table. Okay, or I think some substitution table or something they call it. Same, I forgot. So if we observe that they are making this addition, multiplication and inverse over here. But this is only for two elements. Okay, now using this table, what we are observing is, you can see the observation. The observation indicates that these are all necessary digital circuits that we are looking at. You can see XOR, you can see AND operation, you can see AND operation, you can see one by one. So that's what I'm talking about. So given a field, you can make sure that that follows a particular certain permutation, certain combination, based on which you can define certain digital operations on top of those data, and you get the desired output as and when required. Right, so that's the application of this field. But this is only with two elements. So now suppose I look at Z5, where there are 5 elements, 0, 1, 2, 3, 4. Okay. So if you observe there, the same Kelly's table is maintained. How we are doing it? Let's just discuss a little bit on this Kelly's table. You have the elements 0, 1, 2, 3 and the two operators, that's plus and multiplication. Can you see that? And remember, all these are modulo operators. Alright. So these plus and multiplication are basically the two operators on top of it, hoping that this is a field that we are talking about. So we are assuming all the properties are maintained. Now, if you see the addition table, okay, very simply what we are doing is that we are taking the normal addition, like for example, 0 plus 1 is 1. You can see the first row, 0 plus 0, 1, 2, 3, 4 is repeated. Now, after a certain period, for example, you take 4 plus 4. 4 over here and 4 over here. What is the value of it? What you are getting? 8. And now what is the Z5? We are taking as Z5. So basically what we are doing is 8 divided by 5, remainder is 3. So you can see the element over here is 3. So that's how the Kelly's table is formed. It's basically the collection of all the remainders, and if you observe, wherever you have zeros, for example, you can over here as 0, 0 plus 0 is 0, then you have something as 4 plus 1 is, see here, 4 plus 1, that's also is 0, 2 plus 3, which mounts somewhere over here. See this table, 0 plus 0, 1 plus 4, 2 plus 3, 3 plus 2, 4 plus 4 plus 1. What? 0 indicates? Remainder is 0. That means, as it is indicating plus sign, it's actually showing us an information that they are all this pair 0, 0, 1, 4, 3, 2, they are additive inverse to each other. So basically this table, wherever you are getting 0, 0, it's an easy way of finding out what are the additive inverse for this particular set of elements. And on the same manner, if you take the multiplication operation and you form the table, same way. So for example, 4 into 4, the last two elements you check. 4 into 4 is 16. 16 divided by 5. So the remainder is 1. So see the table entry. That's the Kelly's table I told you. So this is basically, we are trying to arrange all the remainders from the operation that we are talking about. First, the operation is multiplication. You can see in the corner it's mentioned, multiplication. So 4 multiplied by 4 is 16. 16 divided by modulo 5 in this case. So it means remainder is 1. So you are taking 1 over here. Now, you check wherever the 1 has come. For example, you can check, you have 1 and 1 is a 1. Then you have 3 and 2, wherever it intersects, that's a 1 over here. And then you have 3 and 2 is again going for 1. And 4 and 4 is going on 1. What does this 1 indicate? The pair that you are looking at, those are the multiplicative inverse. So for a Z5, you can observe that at 1, at 3, at 3 and 2, and at 4. These all has the multiplicative inverse present with respect to Z5. And you go back to the condition that I told you. Which condition makes the multiplicative inverse? GCD is equal to 1. Right? GCD, and in that A is GCD of A comma B, where A is the modulo operator. So 5 comma 4, it's 1. Okay? 2 comma 5, GCD is 1. 1 comma 5, GCD is 1. So it's matching. So basically this two table is indicative to how do I get hold of the additive inverse as well as the multiplicative inverse. And you can see the conventional identity elements is also present over in the last table. Okay, you can see, observe very carefully A and A inverse which has been mentioned, neglecting the 0 of course. And you can see 1, 2, 3, 4, the lower half over here. You can see 1, 2, 3, 4. Along with it, we can get 1, 3, 2, 4. So ideally, this is the process in which we can find out the modulo operator, how it affects a particular field which has certain amount of element, Z5 for that matter. Now, as you can see, the group, ring and field, the classification with respect to the algebraic structure is also mentioned over here, which we had already discussed quite a lot. So we don't need to discuss that much over here. But this is how we are framing the scenario. Keeping this in mind, now we are going to represent it in terms of binary digits. So let's see about the binary digit for that matter. Now you can see, suppose it's 2 to the power 2. When n equals to 2, we are taking 2 bit at a time. Okay, so we have the possible combination as 0, 0, 0, 1, 1, 0, 1, 1. Now, suppose with respect to this, we have to find out the multiplicative inverse of a set which has this data 0, 0, 0, 1, 1, 0, 1, 1. So how we are going to do it? So again, you can see we can form the Kelly's table, forming this addition and multiplication table. And in every cases, you can see it's already mentioned. The blue color part is basically showing us all zeros. Alright, so you can see that this is due to addition. So those are my additive inverse that we look into. Just the same way. Up to this point, we were taking numerical values, integer values. But now we are only restricting between zeros and one, as it is a digital data we are talking about. So basically, we are talking about all the zeros as the wherever it has appeared, those are the additive inverse. On the other hand, wherever the ones have appeared, you can see 0, 1, 0, 1, 0, 1, these all have appeared. They are all the multiplicative inverse and the identity elements have been mentioned over here. 0, 0 and 0, 1. So same thing, it's just a repetition in terms of digital data, nothing else. Alright? Right? So hopefully this is all like at least you are understanding on the process, and this is how we are going to finally represent this whole finding in terms of the polynomial equation. As I was telling you, the linear block codes and all, they are going to utilize this kind of an expression to find out for a particular field, for a particular field with certain amount of data, suppose 2 to the power 8 or 2 to the power 7 for that matter. Okay, so if it is 2 to the power 7, then how to represent that in a polynomial function? Because only if you are representing that field in a polynomial expression, then only you will be able to use the addition, the multiplication, the division, all those operators on top of it. Otherwise, you are not going to use it. Alright, so you will see that one by one how it is to be done. So the process is something like this, just an example for you. So you see that based on that generic expression, suppose this is the n-bit word. I was telling you about the information theory. Suppose this is the message data, 8-bit word. Now, as we know about the polynomial expression, what we are going to do is go back to the previous expression, just like this. X to the power 3, it will always start from 0. It will go till n minus 1. So here, our n is 8. So it should go till 7. Alright, so what happens is, you can see the power is 7. Now the coefficient will be nothing but whatever the entry is here in the message word. So 1 is multiplied here, 0 is multiplied here, same, so on and so on. Now wherever 0 is getting multiplied, those power of x will not be existing. So you can see the final expression is coming as x to the power 7 plus x to the power 4 plus x to the power 3 plus x to the plus 1. So that whole 8-letter word, 8-digit word is now should be represented by an equation x to the power 7, x to the power 4, x to the power 3 and 1. Now imagine x is the input. Just to relate it how it is to be. X is an input. Okay. So that should go through certain degrees of bit registers in order to generate this polynomial at the end. This is the output you are getting, right? The x is the input and you are getting this kind of an output. So you have to arrange the digital circuit. You have to make the digital circuit such that this as becomes an output. Okay, so number of multiple memory elements and all those things should be governed by this polynomial expression. Similarly, if I go about, so if I get a polynomial expression, we can do the polynomial arithmetic on top of it. So basically, if you get two such things, for example, let me just go ahead with this. For example, these two elements are there, fx and gx. Both are generated using the same principle. So as it is a polynomial, we have defined it with respect to field with the operation. We can directly add up. You can see the operation, add, minus and multiplication. All can be done on top of it. So the product, so suppose you have defined a system where you are defining such polynomials and you want to follow certain property of multiplication or an addition, you can easily go on using it for the polynomials and you get the final result out as an output. So this is about the ordinary polynomial expression that we come across. Now we come to the irreducible polynomial. In that case, you can see the irreducible polynomial, the definition of it. In some cases, you can see addition of two polynomial doesn't create a polynomial out of a set. But multiplication might create a polynomial which is out of the set. And that itself is called as the such polynomials are referred as irreducible polynomial, and that is given over here. So there must be some application of it. Again, for the time being, we don't need that much of details over here. But let's see how it is to be done. For example, this is the two addition. See the addition over here. The sign has changed now. We are doing the modulo addition over here. So we have two certain polynomials which are getting added up under a field which is gf 2 to the power 8. Now we have defined what is gf 2 to the power 8. So that means 8-bit numbers, 8-bit digits are there. And you have the two sets of polynomial which needs to be added up. So you can see that how we are representing it. Generic expression. How we are representing it, you please check. So we are representing it because x to the power 5 plus x square plus x. So it means for the other x7, x6, x3 and x to the power 0, those are 0. So you can observe x to the power 5 x square plus x to the power 5 has 1, x square has 1 and x has 1. The rest of the coefficients are all 0, but it should be represented in the form of 0 to 7 because the generic expression runs till n minus 1. And this is also same. We have done the modulo operator and the final outcome is coming as guess what? For the carry. Carry for x squared terms. Yeah, square. It's 1/0. What about the carry? Carry won't be considered over here in this case. In this case, it's like you're doing one. I think I have shown you this over here. So if you check that 1 plus 1, that addition, the second table. So it should be 1 plus 1 should be considered as 0. The carry forward will not be there. It actually is another circuit which will take care. But for the timing, we don't need that carry forward over here. Information as such. No. Yes. Right. So this is about the addition. Same way we can go ahead. And with respect to multiplication also, same thing we can do. We can go on multiplying it. And whichever element we are coming as a coefficient as 0, we can neglect that accordingly. Division also we can perform. The residue we can see, the remainder we can find it out. This remainder will be useful, or the process will be useful again, as I said, for the error control coding. We will see that. You will only see it later, how they are being used. Right? So this is again, you can see how for a polynomial expression, guys, please concentrate. This last element you see, this is where we end. This is Euclidean algorithm on the Galois field. Okay, so in this case, you can see the two elements, x square plus 1 and modulo x4 plus x plus 1. And you are following the table which is same as that of the Euclidean table. So you take the element, the modulo operator, you can see, these are the techniques. You have taken the modulo operator here, and the element that we got divided into, we are trying to find out multiplication inverse. So repeat over here. Same thing we are doing. Until and unless we are getting hard. No. Go on doing it. So the inverse of x squared plus 1 will be something like x cubed plus x plus 1. So the Euclidean algorithm part we have discussed. Now it is the application in polynomial arithmetic. Alright, so that's how it stands. Same here as well. We can take another example for that matter. So the summary of this is, please check this. The finite field can be used to define 4 operations: addition, multiplication, subtraction, division over n-bit words. As I said, why it's n-bit words, as the information theory has told you. The only restriction is that division by 0 is not defined. Okay, so that's one of the conditions. Right? So that concludes the first part of our discussion on this. So we'll come back to primes and the last module next week. I think most probably I'll take one class to finish off a portion of it actually, and that will be the syllabus for your CAT. Right? Thank you.